So the question I want to address today is a very simple one. What temperature do we expect metals and silicate to equilibrate at during core formation? There's been a lot of speculation and whatnot around this, and in fact it's a very important question regarding the partitioning of moderately acidophile elements between metal and silicates, which we see reflected in the present mantle composition. I'll show you the conclusion first, in case you want to take a nap. I know it's after the beer has been served, so maybe some people are getting sleepy by now. The conclusion is that metal falling through a magma ocean breaks up into small drops as it descends. This is not a radical conclusion, it's more or less a consensus view. Metal rainfall can heat the magma ocean of order 1000 Kelvin, and this is the key point in this talk. Thus, metal-silicate equilibration occurs at temperatures much higher than the silicate liquidus, because the magma ocean already starts at temperatures above the liquidus by definition. This heating takes place in the magma, and the metal is subjected to very high temperatures as it reacts with the magma as it's settling through it. And then we've made a new model taking into account these considerations, which suggests equilibration in a deep magma ocean. For a single stage kind of model, we get a number something like 2,000 kilometers deep. So what is the story, or what is the problem that we wish to address here? It's very eloquently expressed in this paper in 2005 by Wade and Wood. And the key thing I want to draw your attention to, they're looking at vanadium, nickel, cobalt, magnesium, silicon, the usual suspects, and the partitioning of these species, particularly nickel and cobalt, seem to indicate that core metal or core silicate metal equilibration in the magma oceans occurred at a temperature which is about 700 degrees C above the peridotite liquidus at around 40 GPa, assuming an oxygen fugacity that's similar to the present-day Earth. However, they considered that it's physically implausible, and they went on to consider other ways of perhaps performing this. What I like to show is that, in fact, this is quite physically plausible, and this is what we expect to occur in core formation. So here's a plot, basically, of their regime diagram of where the equilibration fits in temperature-pressure space. There's a PT path in their model of core formation, which is consistent with partitioning at constant oxygen fugacity. And then there's the peridotite liquidus, which is way, way, way down here. So how do we get core mantle equilibration at these high temperatures? So let's start from the beginning. We have a proto-Earth, or proto-planet, if it's another planet. This should apply to all planets. We have an accreting planetesimal. It could be differentiated or under-differentiated. The point is that even if it is differentiated, as the metal part of this accreting body falls through a magma ocean, as it descends past several diameters of its initial size, it breaks up. It breaks up and it turbulently mixes with the surrounding magma. And this is, this is where we should really focus our attention. Here are some experiments shown by Renaud Degane's paper recently. Also, we've seen a lot of numerical results. But what happens at the small scale? This is actually where the rubber meets the pavement. This is a model based on Hiroki Ichikawa's PhD thesis in ENS Lyon a few years ago, published in JGR in 2010. So we take this drop of metal with a surface tension, and we let it settle through a silicate magma. This domain is periodic. As bits fall through the bottom, they reappear at the top. And so it's completely periodic boundary. And after a while, you can take a big drop, and it breaks up by turbulence into smaller drops. Smaller drops, of course, can grow by benefit of surface tension, but only up to a certain size. So there's an equilibrium raindrop size, which is dictated by a balance between surface tension and breakup. This is what a raindrop looks like in detail. It actually doesn't have this characteristic tail like I'll show you in the next cartoon, But in fact, the flow is kind of laminar around here, but there's adequate circulation. These things will equilibrate in a very short time with the surrounding fluids. In these models, it's also possible to calibrate the settling velocity of the metal, the average settling velocity versus the radius of the raindrops, and this is the kind of result you get here. You see it's something, a fraction of a meter per second, and the raindrop size is something like a centimeter or two. The settling velocity is also a function of the volume fraction of metal. If there's more metal, then you get a smaller velocity because there's less magma to fall through. So you have actually this dependence, which is a flux. If you put this into a calculation and just a rough order of magnitude estimate, it takes about a year to drain about 1,000 kilometers of iron bits from a magma ocean. That's just the order of magnitude argument there. So what happens here? So this stuff falls into the magma ocean, it mixes and becomes raindrops on the order of a centimeter in scale. And as this rain falls to the bottom, it will pond above the solid mantle. Here I've just kind of drawn a cartoon where impact makes a melted cavity. Of course, there could be a long-lived magma ocean here. The same arguments actually apply in that case. But the metal ponds at the bottom of this molten cavity. And as the rain descends, it's equilibrating every few meters that it falls. So just as the metal falls to the top of this metal pond, it will have retained or imparted upon the magma ocean at that depth the particular equilibration pressure and temperature conditions that are recorded in that event. As the rain falls, in the wake of that, you'll have a vigorously convecting magma. But the metal rain itself actually stratifies the magma ocean because it's heavy. And so you have to wait till the rain falls out before it can convect. Another consequence is that the bottom of the stuff should be dense and the top is buoyant, and that should become more clear in the subsequent. And then eventually the metal sinks to the core. It doesn't really matter how in this talk. A process that could take between hours and millions of years. So what do I mean by heating of the magma by metal fall? You can just do a simple argument of the change in gravitational potential energy before the metal falls. So if you take the mixture of metal and silicates and integrate over an inner and outer radius of the magma ocean, and then afterwards you have a separation into a metal pond, so the inner radius to the radius of the pond, and then integrate from the pond out to the outer surface. Of course, this is primed, and the gravity changes actually due to the separation. But what you get, and this is very, very simple to do, for 10% metal in a 1,000 kilometer deep magma ocean is something like 1 million joules per kilogram. If you convert that to heat, all of this is actually dissipated turbulently and becomes heat. You can get something like on the order of 1,000 kelvins. So heating is cumulative. The more rain falls through a magma, the more it heats, right? The first raindrops to rain out generate little heat, but later rains, if it keeps on raining in a certain spot in the magma ocean, a certain depth, it heats more and more. So we can do this very simple model where we imagine that the temperature is constant with radius before the rain. It doesn't matter. I'm just putting a straight line because it's easier to see. After a little bit of rain, the temperature is increasing from the bottom, and it's also increasing downward from the top because the raindrops will have fallen out of the top, but down here there will have been more cumulative rain falling. As well down here, as the metal's ponding at the bottom, the raindrops will have fallen through magma that the previous raindrops fell through, and therefore will be hotter. And then we can take this to completion, where the metal is here. It's basically exhibits a temperature gradient which is convectively stable. It's actually going to be reinforced by the fact that oxygen and silicon and things like this are going to partition in the metal at higher temperatures. So you're going to have a convectively stable metal pond, which is thermally stratified and compositionally stratified. And then you're going to have a magma ocean which is left behind, which is highly convectively unstable. And then, of course, you can estimate what this temperature increase is due to the change in gravitational potential energy, and you should be in the ballpark. We can also do a more complicated model. Gravitational acceleration, pressure, all these variables are changing as the metal is settling out of a magma ocean. So it's useful to consider a more complicated case where we track these things. So we've also performed a one-dimensional self-gravitational numerical model, and we've used the micromechanical models, the raindrop models, as inputs into this. We also have elemental partitioning according to experimental data. We have a huge library of everything, basically, that's ever been published. And we try it all. We put all of it in there and see what comes out. So here's what we get for the temperature. So here's the initial temperature, which is not uniform, but you get this kind of temperature profile like I showed in the simple model. So this is what our complex model reproduces. The broken line here is the simple model I just described. So it does a pretty good job, actually, of reproducing the results of the complex model. If you look at it in detail, there's some interesting things that happen. Of course, here's the density change with time. So we go from a mixed curve to one where the iron is separated out into a pond. This is the purple curve, is the last time frame. The pressure is actually pretty constant. It doesn't change much, but the gravitational acceleration does actually change quite a bit. So there's a lot of things we can look at in these models. But now the question we ask is, what is the effective equilibrium PT condition at which this stuff is occurring? And so the idea is that we compute the partitioning of all elements in the numerical model. We back calculate the pressure temperature conditions from the resulting average composition using the partitioning models. And this yields an effective PT condition. The interesting thing is that the results aren't really sensitive to model variations or data. This is just a small subset of the data that we use. And this is what you get here. This yellow dots are basically following the solidus, and these blue dots are the effective PT conditions, and these are error bars, which are calculated based on variances from the partitioning models. And then this red curve here is the simple model that I described earlier, just using that. So what you get is effective pressure temperature conditions, which are imparted into the magma, which is left behind, which are much higher than the liquidus, actually. And the pressures are also much shallower than the actual depth of the magma ocean, the nominal magma ocean, if you extrapolate that adiabatically up to the solidus. So these are the key results. Effective temperature can easily be more than 1,000 Kelvin above the solidus. There's no problems to explain this phenomenon, which was explained by Wade and Wood, this high temperature, 700 or more above the liquidus. The effective pressure can be more than 2 times smaller than the base of the magma ocean. So the pressure you're actually seeing in the moderately siderophile elements is not actually the pressure at the base of the magma ocean. Our best fit to the data, assuming a single-stage core formation, and the typical abundance is accepted for moderately siderophile elements in the Earth, gives us something like 2,000 plus or minus 500 kilometers deep. There's a large error bar still. And the kind of alternate scenario proposed by Wade and Wood, and later by Wood and others, of lower temperature equilibration with variable oxygen fugacity is not necessary to fit the data. Of course, we cannot rule this out, and there might be good reasons to believe that heterogeneous accretion will deliver increasingly oxidized material to the Earth at later stages. However, from this kind of consideration, we do not actually need to have that to fit the data. There's a little bit of spin I can add to this. One is that if the effective T is only 700 Kelvin above the liquidus, and our model is consistent with 2,000 kilometer deep magma ocean single stage, it actually favors smaller metal fractions settling through deep magma oceans, which is compatible with long-lived magma oceans, which do not freeze very quick. They freeze much slower than a black body, and perhaps argue for the importance of a proto-atmosphere in blanketing the Earth during accretion. And with that, I'll just leave the conclusions and take questions.
Thank you very much. We have time for one quick question.
May not be quick. I think you're making a good point, and I think there's no problem with the moderately siderophile partitioning. Yes, you can do it at high temperatures, that's fine. That said, I think you're overstating the significance of the model for two reasons. First, because the total energy of accretion of the Earth is 10 times larger than the energy of core formation. That doesn't mean the energy of core formation is negligible, but it means you get a lot of heating anyway just from the impact events. The other thing is that when you gave your 10% number for a 1,000-kilometer thick ocean, I hope you're thinking about a global magma ocean, because that's what you should be thinking about,
right.
In which case it's getting damn close to a giant impact. It's not planetesimals. Planetesimals will not do what you're suggesting because they will get extremely diluted. I'm talking about planetesimals 100 kilometers in size. So yes, you have a good point, but it's only for bigger objects.
Yes, so basically what you should think of this is that it's a lower bound, in fact. The energy that you get from core formation is smaller than the total energy available during Earth's accretion. So I totally agree with your statement. As far as the spin, of course, yeah, I was adding some hyperbole and some spin to the story. So I don't necessarily believe all of this, but the key result is that high temperature is no problem.